peers and colleagues. My name is Chris.
I'm Tom.
And I'm John.
And today we're here to talk to you and inform you about the dangers and what goes on with lake turnover, mixing, the stratification thermal decline, and the effects that it has on fish and aquatic species. I'm going to turn it over to Tom to elaborate some of these with the diagram.
So we're going to look at two basic concepts of stratification and lake mixing. I'm going to explain the terms, and then Chris is going to explain their effects on fish. So we've got the lake stratification, which happens in the spring. In the spring, most of the lake, right when the ice comes off, is all a similar temperature. The water is pretty homogeneous. And then we've got the thermocline forming, where the thermocline gets deeper as the season progresses. The thermocline's going to get deeper. And we've got the other situation of stratification we have is the water runoff creating a thermal bar. The thermal bar comes from the water is going to be in the lake right after the ice comes off. It's going to be around 35 degrees Celsius approximately. We've got the warmer runoff, which can form this vertical bar with warmer water along the side of the lake. We've also got our other solution, our other scenario is lake mixing. We've got the wind direction blowing across the lake. This occurs in the fall. So we've got the surface temperature approaching the temperature of the hypolimnion. When those two temperatures are getting close together, we need a physical effect, such as the wind blowing across the fetch of the lake, the longest portion of the lake. So then this is going to blow the wind up. It's going to blow the water up on one side of the lake. We all know pressure is proportional to depth. So we did a few equations here. Once we have the water built up on this side, if the lake is 22 meters deep on this side and the water's been pushed up to 23 meters on this side, we now have 215.82 kilopascals on this side and 225 on this side. So you can see how that is going to push down on this side and create a turning effect of the lake. In this diagram over here, we're explaining how turbidity affects a lake. We've got turbidity at the top of the lake from eutrophication causing increased plant growth. Plant decay creates hypoxic conditions in the hypolimnion, and the sun radiation causes warmer temperatures at the top of the lake. And we've got the low oxygen levels at the bottom of the lake. So I'm going to hand you over to Chris now, and he's going to explain about the effects of this on fish.
Alright, before I get too in-depth, I'm going to cover the basis of hypoxia. With hypoxia and oxygen depletion, it's a phenomenon that occurs in the aquatic environment when dissolved oxygen becomes reduced and the concentration gets to a point where it's detrimental to the aquatic organisms living in the system. Dissolved oxygen is usually expressed as a percentage of the oxygen that would dissolve in the water at the prevailing temperature and salinity. An aquatic system that lacks dissolved oxygen is termed anaerobic. Reducing or anoxic system with low DO, fish cannot live below the 30% DO saturation rate. The hypoxic zones and the part without oxygen is termed dead zone because only anaerobic conditions occur there. Now, it's important to note that hypoxia does not affect all fish the same. With a specific study done in Lake Erie, they looked at a bunch of different fish species. With perch, for example, they were more resilient and they didn't get affected as much by this hypoxia. Meanwhile, the round goby and the port trout species, they were affected to a more significant degree. Now, fish have two primary responses to lower dissolved oxygen levels. They've got their secondary lamellae, which increases the blood flow, which in turn increases the respiratory, and in short term, they release blood corpuscles from their spleen, which in turn increases the blood unit per volume, which increases the warmth. Now, they've got their primary lamellae also, which is there to increase the ventilation rate, to increase how much water contact gets with the gills. Water is forced through the tips of the lamellae, and when the water flow is high, and that's the result. Now, looking at this picture here, we've got the low O2 here, this region, and we've got warmer waters with higher oxygen, and they're warmer because of the sunlight and the vegetation. With fish, in a perfect example, we've got the low O2 pushing the fish up, meanwhile the warmer waters push the fish downwards. This creates a suitable zone for fish, although when there is no situation with no food, they can dip down to the benthic regions perch specifically in a study I looked at, and they dip down to the hypoxic regions to get food if necessary. But generally, it creates a suitable layer for fish to live in this particular example. Now, going over here, we're looking at a lake again, and we draw the layers here one more time. How with the low O2 and the high O2, but then with mixing occurs, that goes on, and then we've got sufficient oxygen levels after the mix. Basically, fish can roam anywhere, but they do prefer to go into the deeper regions of the water. Now, looking at this diagram again, same instance of a lake. We've got the fish that enjoy spawning in warmer, shallow waters, and also with more vegetation, we get more hypoxic conditions. Instances where fish can go to deeper areas because of less eutrophication and less hypoxia. And now I'm going to hand it over to my colleague John, which is going to explain some more effects.
He's just going to explain that a shallow lake is much different than a deep lake. The shallow lake has no stratification whatsoever, causing a lot of plant life and macrophytes to grow. Eutrophic lakes are generally shallow lakes. And where the deep lakes, they have three layers: the epilimnion, the metalimnion, which is aka the thermocline, and the hypolimnion at the bottom. Pretty straightforward. Now I want to talk to you about a common misconception among people. Zebra mussels absorb a lot of the turbidity in the water, causing it to clear up in the water. And people think that the lake is very clear and healthy, which really isn't the fact, because there's a lot of phosphorus, a lot of nitrogen, and a lot of cultural eutrophication, which causes nutrient pollution. And I'm going to turn it now over to Tom.
So we're going to explain now a real life situation. So Lake Simcoe, as we all know, right near Barrie here, Lake Simcoe has an increased, much too much phosphorus loading. Lake Simcoe right now has approximately 80 tons of phosphorus being dumped into it each year. So that's equivalent to more than 3 dump truck loads of phosphorus. Our goal for phosphorus is more like about 35 to 40 tons of phosphorus to be introduced to the lake annually, maximum. The problem with the phosphorus loading is eutrophication. But as John said, with the zebra mussels, people think that Lake Simcoe is very healthy right now. They look at it, they can see down, the water looks nice and clear, so it does cloud their judgment, and they think that the lake's actually cleaner than it is. Over to Chris.
Now we're going to deal with some of the proposed solutions and kind of a concluding basis for this. In terms of protecting our waters from hypoxia, we can minimize the use of fertilizers and manage them properly. Excess fertilizer washes off in agricultural applications usually, and that really contributes to the hypoxia. We can remove nutrients from wastewater and runoff before they are discharged. This will help reduce, and these sources contribute a lot to the effect of the hypoxia. Now, it's very important that we can reduce the amount of electricity and the number of miles driven. This effect that it has in power generation and power plants, they generate nitrous oxides, and they're transformed into nitrates in air, which are deposited around the country, especially in certain regions. We can practice clean boating. This includes using clean boat engines, not dumping your beers and canning them, just not polluting our waters, and reducing discharge of sewage water. We can preserve land adjoining rivers and streams. In this case, land is often a riparian buffer, and it can play a vital role in what's going on in preventing nutrients and the wash-off fields that can stream from the reaching rivers. Basically, by reducing this, we can provide habitat for wildlife and migrating birds, and it improves the overall health and beauty of the stream.
So, in conclusion, these are the two main concepts that we've got, and as you saw, the phosphorus loading causes eutrophication. These are pretty much the two key concepts, and we hope you learned something and enjoyed our presentation.